Hi everybody, let's finish off our look at ionic naming with a study of hydrated ionic compounds. So it turns out that there are some special compounds that have ionic crystals with water molecules stuck inside, and they have a specific number of water molecules. So these water molecules are sometimes called waters of hydration, and there is a certain number of them per group of atoms in the formula unit. So for instance, if you had sodium chloride, NaCl, NaCl is just the most simple ratio of this formula unit. And let's imagine that you had 10 groups of NaCl. If you had 2 water molecules for every 1 group of NaCl, and you had 10 of them, then you'd have 20 water molecules, because you'd have 10 times those 2 water molecules for every 1 group of NaCl. So we'll see what that looks like when we get down to some examples in a second, and we'll also have a chance in class to separate out some of these waters of hydration from ionic compounds. So how do we name them? Well, when we name them, we simply write out the name of the ionic compound without anything to do with water, and then we add in the number of water molecules using our Greek prefixes that let us know the number of water molecules based on the prefix that we see. So for instance, let's dive in with this problem down here that has PbClO4 and you'll notice that to separate our water molecules from our ionic compound, the convention is to put a dot like this. So let's try naming this. When we name the anion first. And the anion here is ClO4. So ClO4 is not found on our polyatomic ion list, but it looks a lot like something that is, which is ClO3. So if ClO3 is chlorate, then ClO4 must be perchlorate. Next up would be to ask ourselves, does our cation require a Roman numeral? And the answer is it does, because it's a transition metal. It's in the middle of the periodic table. And furthermore, Pb is one where we know 2 names. We know the name of Pb in just a classical Greek way, and we also know it with Roman numerals. So we need to figure out its charge. To do that, let's look to the anion. The anion never lies. So ClO4 has a -1 charge, but there are 2 ClO4s. So that means the entire negative side of this compound has a -2 charge, which means the positive side must be +2. So we could either name this lead-2, or another word for lead-2 is plumbus. So either lead-2 perchlorate or plumbus perchlorate. And then we're going to finish off with the hydrate part. The hydrate part is where we use those prefixes. And you'll notice the prefix for 3 up here is tri, right? So that becomes trihydrate. And so we really have 2 names. The 2 names we could have are lead-2 perchlorate trihydrate or plumbus perchlorate trihydrate. But you'll notice we're naming the ionic compound first and then putting the hydrate on the end. Looking at number 2, let's name the anion first. So the anion is NO3. NO3 is on our list. NO3 is simply nitrate. Ask ourselves, does this cation require Roman numerals? No, Mg is always a +2, so we can simply name it as magnesium. In fact, if we put Roman numeral 2, we would be incorrect. Don't do it, that's not good. Okay, so we've got our thing named, it's magnesium nitrate, and now all that's left is to name our hydrate. The prefix for 6, if you find it up here, is hexa. So we have magnesium nitrate hexahydrate. Let's try one more going this direction. So SnCl2. Cl2 is not a polyatomic ion, it's simply an anion. We know that anions always end with IDE, so this is simply chloride. Now we ask ourselves about our cation. Does our cation require a Roman numeral? Yes, it does, because it's a transition metal, and we have 2 names for it. So what is its charge? Look to your anion. The anion has a -1 charge, but there are 2 of them, so that means the total negative charge here is -2, which means the total positive charge must be +2. So that means we could either call this thing tin-2 chloride, or we could call it stannous chloride. Either one works, and then we come over to our hydrate. 4 has a prefix, which is tetra. and then we put in the hydrate. All right, let's go the other way. So what if we wanted cupric chloride dihydrate? Well, let's just name it the way we know how to, and the way we know how to name is to write in the symbols for both of these compounds and then cross the charges. So chloride is Cl-1. Cupric is something you could look up if you needed to. It's Cu with a +2 charge. So when you cross those charges together, you're going to get Cu, Cl2, and then we're going to add on the dihydrate part. So di means 2, so we're going to have 2 waters. If you're well hydrated, you have enough water. So hydrate means water. Let's look at manganese 2 bromide tetrahydrate. Well, bromide, again, bromide is a single anion because we see that ID ending. So this is simply Br. Br as an ion has a -1 charge. Manganese, be careful with this one, manganese is not Mg, manganese is Mn. Mn is a transition metal, so fortunately they tell us its charge, which is a +2 charge. Cross those together, you're going to get Mn, Br2. How many waters do you have? Well, it's tetra. The prefix for tetra is, well, the prefix tetra means 4, so 4 H2Os. And finally, chromic bromide heptahydrate. Again, bromide is a single anion because it has an ID ending. So we're looking at Br-1. Chromic is something you could look up if you needed to on your resources for the whole year. It's Cr with a +3 charge. So Cr +3. We can cross those together and we will get CrBr3. Then how many waters do we have? Well, hepta means 7, so 7 waters at the end of the day. So again, this is very much just kind of a review of ionic naming. All we're doing is tacking a hydrate on the end, but it's pretty straightforward with those Greek prefixes representing the numbers.